Okay. Good afternoon, everyone. Amartya is back. He's going to speak about the homotopy theory of Kohn complexes.
Yeah. So today I'll be speaking about today's website about configurations on the concordant model structure. Yeah, so here's the plan. So I'll be beginning with standard concordant. I'll be talking about Kohn complexes. Then I'll introduce. There'll be some things that we already have worked on. So so I'll kind of give a recap and then then I'll also talk about the X infinity factor and then anodyne extension. So it's basically the first two sections of the first chapter. So so I'll kind of begin with giving a quick recap of. Okay, excuse me, just is there an echo?
No.
Wait.
Yeah, can you hear me now? Okay, sorry. So, I'll begin by giving a quick recap of saturated classes. So, class monomorphisms and the category of sequential set is said to be saturated. So as I said, this is a quick recap, and I'll be defining saturated sets in a bit of a slightly different way, but here it is. So it contains all the isomorphisms. Then A is closed under push-outs. There is so if we have this one, so if this is a push-out diagram, and I is in a set of morphisms, then I dash also. So this is what closed under push-out means. Okay. So A is closed under each tags. There is again classical diagrams everybody is familiar of. Yeah, so I'm just bringing a quick recap. So I have this diagram. So says that this is identity and this is identity. Then so if this is a commutative diagram and I dash is in A, that implies I is also. So then A is closed under B tracks. Sorry, we talked about that. So A is closed under coproducts. There is if So if we have a family of monos, this is our index set, is a family of monos with ik and a. For all k key, uppercase key. Then the following morphism is also in A. Then A is closed and co-complete. That is if yeah. So if this is a countable family of morphisms in A, then yeah, take the limit. This also has to be in A. Right. So this is equivalent to other. I mean, yeah, this is equivalent to a definition that we have in Cisinski. But yeah, I just wanted to give a recap. So now, okay. So yeah, the intersection of all saturated. Or let me say this: the intersection of all saturated classes containing a set of morphisms. Okay. So okay, I'll write this: the intersection of all saturated classes containing a set of morphisms. So let me call it, say anything, say F is called saturated class generated by F. This is the terminology that we have. So, okay. So yeah, so let me give an example. For example, if we take, so if, okay, so if this is an arbitrary monomorphism in simplicial sets, then yeah, then we have the following push out square. Okay, okay. I'll give a sketch of the proof. Let me write it out first. We have the following push out square. It's not that hard to see. Just give a hint. I won't get into the details. So this is a push out for n greater than or equal to 0. So in order to prove that, so you can, yeah, we can use the truncation functor. So that is the idea. So using the truncation functor, we can prove this. So that's the hint that I was talking about. So yeah, so let me tell you what these things are. So this is, so yeah, so this is my notation for the set of non-degenerate n simplicities of X, which are not in A, right? So that's why. Then, yeah, then we have X, we can write X, write it as a colimit. and we call, I'll just name a few things and we'll see why. So this is, we take the limit. Okay. Then, yeah. So, yeah, this functor that we have, so this is precisely the initial mono that we had. Initial monomorphism that we had. Right. So yeah, so from this we can prove, so yeah, this proves that the saturated class, because this is an arbitrary monomorphism, the saturated class generated by the family, just boundary inclusions, boundary maps, is the class of all monos. Yeah, so this was the example. So yeah, so yeah, I will give a definition of anodyne extensions. So that is, although equivalent, a bit different from the way Cisinski does it. But this is the one that I prefer. So let me. So the saturated class is generated by the So this is the family or inclusions is called the class of anodyne extensions denoted by, so anything, doesn't matter. So let me call it this. Okay. So yeah, then so remark maybe. Let me add this. So if M is a like class of morphisms in the category of simplicial sets, then the maps with left lifting property again with respect to all morphisms of M, that is like, so this is the notation that's standard Cisinski. So this is saturated. So this is saturated. So this was a remark. So okay. So here's a proposition. So the following saturated class of classes, surfaces coincides. So yeah, I won't give a proof. So yeah, there is something that I didn't mention at the beginning. So yeah, for most part of the talk, the canonical reference would be, so yeah, Gabriel Zisman, and also I think there are some notes by Jayal and Tierney. So yeah. Anyways, so the following saturated classes coincide. So let me give them some names. Set of all inclusions so this is our first class. The set of all inclusions I don't need this. Where X is a simplicial set and Y is a subcomplex of X, and epsilon as usual is on Y. So done. And so okay, yeah, I've given it a name and ano. So these are our three classes. So these three coincide. So yeah, for the proof, yeah. So yeah, it's a bit of work. So for that, yeah, you can refer to Gabriel Jesman. Okay. So now I'll define a configuration. So a map is a configuration if and only if it has right lifting property with respect to all anodyne extensions. So this is the definition that I have. So yeah. So now now I'll talk about a few theorems that we will end up using towards the end of the talk, and we'll be proving things about the so yeah, we'll be proving that we have a concurrent model structure. So any map. So okay, from A to B in the category of simplicial sets has a so it has a factorization of form where I is an so I is an anodyne extension, and P is a vibration. So yeah, you have this factorization. So yeah, we'll prove this. So yeah, let's consider the set of commutative diagrams. So let me draw them first. So yeah. Okay, so yeah, let's consider this. Let's consider this sort of commutative diagrams. Now, if we sum over n, if we sum over L, right? So wait, if we sum over L, so yeah, so let me name the set L. So set. Yeah, let me write it like this: the set L of commutative diagrams. We have the set of L of commutative diagrams. So now summing over L will get something like this. So just summing over L. So yeah, this is so we have this map. So now yeah, this is an anodyne extension. Yeah, this is an anodyne map. So yeah. So yeah, using the definition that we had. So now we take the push out. So now we take the push out, then yeah. This, and we'll have this. So, okay, maybe let me try to draw this. properly. Books. Wait. Just give me 1 second. Pencils to business to some problem. It is working. Yeah, it's fine. It's working. I'm sorry. So yeah. So you take the push out square and then you have this where yeah, this will also be, so this map will also be anodyne. Then so yeah, because of closure property that we have, then we'll end up with a commutative diagram. This yeah, from this right here will be a commutative diagram. So I'm not sure how do I use the pointer, but yeah, so maybe I'll draw it again. So yeah, we'll have this will be a commutative diagram. Right. So this map right here, call it F dash. Okay. So yeah, so now we repeat this process with, so the way we did it with F, we repeat the process with F1, then we'll have the following diagram. So if you work it out, you'll get the following diagram. Yeah, let me check if my notation, yeah, my notation is fine so far. So I've not messed anything up. So yeah, we'll get a factorization of this form. Yeah. So this is my notation. Yeah. So we'll have a factorization of this form with J1 being anodyne. Now let's yeah for like for just aesthetic reasons, let's call x0 to x to be x and f0 to f, and let's define e to be the limit, and let me call, yeah, let p be the map induced by Fn on each xn. Okay, so then we'll have, yeah, then we'll have the following commutative diagram. It's not that hard to see. We'll have the following commutative diagram where I, right, I've been calling it J, so okay, let me stick to J. J is anodyne. Just try to. J is anodyne. Now, so yeah, so we just need to show that P is a vibration. So that's the thing that remains. So we'll again consider a commutative square. So let's consider this. We just need to show, yeah, we just need to show that there exists a filler. So that's the way we proceed. So now, okay. So now as, okay, let me write this. As this horn has finitely many non-degenerate simplices. So we can factor through xn. So yeah, that's what I mean. We can factor through xn for some n greater than equal to. So then we'll have the following diagram. Right, and okay, reach C. So this was, let me call this H. And yeah, so we can extend this. And this will be my Fn plus 1. So yeah, we'll have the following lifting. Right. Wait a second. Wait. This is a sorry. We'll have the following lifting. So yeah, so that implies that we have a so that implies that this diagram has a diagonal filler, which is it. Cool. So yeah, there's a corollary, important corollary that we'll also use at some point. So if we have so if this is an anodyne map, okay, no, let me write it like this. Yeah, so this is anodyne if and only if it has the left lifting property with respect to the class of all vibrations. Yeah, that's just a problem. Sure. So I won't give a proof. It's not that difficult. It's so okay. So talk about another theorem. So yeah, now we'll see that we also, so yeah, for any map in the category of simplicial sets, we'll also see that there's a factorization into a monomorphism and an acyclic vibration. So let me write this. Any map of simplicial sets admits the following factorization. So yeah, this is my map where I is a monomorphism and P is an acyclic vibration. Right. So yeah, we'll also prove this. Yeah, we don't need to actually because it is this. I mean, yeah. So it is. Yeah, it is identical to the previous. So yeah, I'll just write it. So it is. So we just need to repeat the proof of the previous theorem using using the family, using this family, right? So use the family. Let me just write this briefly. Use the family instead of in the proof of previous theorem. Right. So yeah. So yeah, now I'll give a definition of a complex using whatever we have done so far. So yeah, so a simplicial set X is called a complex if so the map from it to the terminal object is a vibration. Right. So historically, I think it's worth mentioning that historically complexes were defined originally in the cubical setting. So this is something that I felt worth mentioning. So let me give a few examples real quick. Yeah, so the most, like the classical example, the canonical kind of an example that was, I mean, so yeah, so Khan complexes basically came as abstractions of singular simplicial complexes of topological spaces. So that is an example. So singular simplicial complexes of topological spaces. So yeah, basically Khan complexes are an abstraction of this. Then another example that I can think of right off the bat is that if you have a group part, this is my category of group parts, then the nerve, I mean, yeah, an infinity group part, of course. So I don't know. So let me write. No, I'm sorry. Yeah, a group part, not an infinity group part. As you're taking the nerve. So yeah, so if you take the nerve, so it's a Khan complex. Right. So Okay, let me think now. So, okay. So, okay, let me talk about. Oh, yeah. So, a lemma. So, if we have a vibration, if you have a vibration, let me call it P, is a vibration, then there exists a surjection C to B such that in the following pullback square, so a pullback square looks like this. In the following pullback square, if P is a vibration or an acyclic vibration, no, I mean, yeah, P dash, then P is also the same. Yeah, it's also a vibration or an acyclic vibration. Right. So yeah, I won't give a proof for this. Well, it's not that difficult. So now I'll kind of, yeah. So I had initially thought of talking about, yeah, so defining the notion of a bundle with fiber. So maybe a digression. So as you would have noticed, I had put that in my contents plan. So, okay. So, and yeah, this digression is because, so when I was learning this stuff, yeah, this was kind of the order that I learned it. So I don't know. So let me define this. A bundle with fiber F in the category of simplicial sets is a map. Let me call this phi. Yeah. E to X such that for all n simplices of X, there exists an iso. So let me call this lambda. So we have the following isomorphism. So just projecting it. Right. So we have the following isomorphism. Precisely. So now, okay. So now, okay. Let me also do this. So let me define y. Be following. So just summing it all. So then the map y to x is a surjection, right? So then since, so I think it's important to write this since y. So since this map is clearly, yeah, it's a vibration. So I don't want to write clearly. When f is a, so when f is Kahn, it's a Kahn complex. So it follows from the previous lemma. So the lemma that I didn't give a proof of, but yeah, the previous lemma that so a bundle, yeah, so it follows that a bundle with Kahn fiber F is a vibration. So this is what follows. So let me give an example. So maybe, yeah, and yeah, so I won't define everything that I'm, so I won't define the example that I'm going to do here. So for people who know better, otherwise it's okay if you don't. So if G is a simplicial group, so I don't know. Wow, what? How can I give an idea about that? So Yeah, so okay, let me just proceed with this. And P is a principal G bundle. Then clearly P is a bundle with fiber G, and thus vibration. So yeah, I won't get into the details. I won't define like a lot of stuff that's not been defined. But okay, so yeah, that was an example. So now we move on to the quickly to the second section, and I can see already that we're already running behind schedule. So let me try. So yeah, now I'll define I'll define functor complexes, function complexes rather. Sorry. Okay. So okay, so for X and Y in the category of simplicial objects, right? So let me write it like this: category of simplicial objects, and yeah, and C must have rather than let me write C has small co-products. The function complex is a simplicial set, or maybe with the set of n simplices being the set of maps okay. So and this is co-powering. Yeah, I think so should I define a co-powering or fine. So co-powering of simplicial objects over simplicial sets. So yeah, what do you guys think? Should I define a co-pairing? So I'm waiting for. Let me see. Oh yeah, let me just give a quick. There's no harm in that. So okay. So what do I mean by co-pairing? So yeah. So I have a. So let me have a closed monoidal category. So yeah, by a closed monoidal category, it is like just a symmetric monoidal category that has an internal. So okay, let me write that as a comment as well. That has an internal hom, and so okay, so let my okay, so that means that so okay. So and yeah, you'll have an isomorphism. So if you have an you'll have this isomorphism. Category is V. And this is your internal hom. Okay, and C is our let me call C to be a V enriched category, right? Then yeah, so then co-power of an element of C by say K V is an object which I denote like this, and C with I think you have this as well. Right. So yeah, so this is what I mean by co-pairing. over simplicial sets. Right. So this is what we mean by function complexes. So okay, so now I'll give a quick recap of like homotopy. So let me call it simplicial homotopy. So okay, so for a simplicial set X, yeah, we know that this is the simplicial cylinder object. Then left homotopy. So this is my this is my acronym or whatever. No, this is my this is what I mean by homotopy. Between, so we have these morphisms, isomorphism, the simplicial cylinder Y such that the following commutes. Right. So yeah, so similar to a simplicial cylinder object for a yeah. So okay, let me see the way I wrote it. Okay, yeah. So for a Kahn complex, so yeah, again, let me call it X. Its simplicial path object is the function complex, right? This is right. Okay. So yeah, now, so yeah, if there's a left homotopy between the morphisms, we denote this by as follows, right? So a right. So now I'll define a right homotopy. A right homotopy. So let me see. Okay. Right homotopy. We call this R. Between, again, the maps remain the same. Is a morphism such that the following diagram commutes. So let me draw it real quick. Yeah, and if two maps are left, I mean, yeah, right homotopic, we denote that by F. So we denote that by just writing an R over the symbol. Okay, so yeah, so two morphisms are homotopic. So we say that they are homotopic if and only if they are both right homotopic and left homotopic. Okay. So now I'll define homotopy equivalences. So a morphism is a left and respectively a right homotopy equivalence if there exists a morphism and and left and respectively right homotopies. This and this. Okay, so now we switch our attention a bit. So what do you want to show that? Okay, so if Y is Kahn, so okay, so let me write this as my claim. So if Y is Kahn, then Yx is also Khan for X and Y simplicial sets. Right. So let's move on with that. So yeah, so this is my claim and I'll put that. So now let's okay, yeah, let me think a bit. Okay, yeah. So suppose I have, so yeah, let me consider this. So let this be a mono, and we have this map. And let's consider the following pullback square. So I'll define all things real quick. Oh, okay, sorry. Then, yeah. So yeah, so KP, so KP. So yeah, it is the corresponding object of diagrams of the following form. This KP. So yeah, so we. Okay, so it is just an object of diagrams of this form. Okay, so now the following commutative diagram. So yeah, this gives rise to a map, like because this is a yeah, so because this is a because this is a pullback square, so we get a map of this form. So this is our notation, right? So this is the notation that I'll be using. So yeah, so we get a map of following form. So now, so this is the key theorem for the claim. So this is the claim that we're interested in. And the theorem is the following. So if P, so everything's as defined above. So if P is a fibration, then the map defined of this map that we just defined is fibration, and this map is acyclic if K is anodyne or P is P is our fibration, so or P is acyclic. Again, I won't give a proof for this, but yeah, so like for most of the things today, yeah, it's like Gabriel-Zisman and Gerald's notes. So yeah, so a corollary of this will be the following. So if we have if this is a fibration, so is for anyway. Okay, cool. So here's a quick observation. So for symmetric monoidal category, so let me call it this. So yeah, maybe, okay, wait, I'll talk about this if I have time. Not get into this will take a lot of time. So I'm already out of time. Okay, so for monos, okay, so we have the following monos. So yeah, let me introduce some notation. We denote, so let me call this notation. We denote the inclusion. So set and sorry. So we denote this inclusion by so let me think of a symbol of, let me just call it star. Okay, so yeah, we can prove that again. Again, this is something that we can maybe take as an exercise. So if J, which is a map, like, yeah, we defined J, right? So if J is a mono, is anodyne, so is this inclusion, right? Yeah, again, for the proof, I refer to Gabriel's map, so you can find a proof there. So now, as a very important, maybe a consequence of the previous theorem, is the covering homotopy extension property, which I'll CH P for fibrations, covering homotopy extension property for fibrations. So let me state this. So we have a fibration and a homotopy. Okay, then suppose the map X to Z is a mono, and we have another, yeah. So yeah, if it is a mono, then there exists a lifting, which is the following: is a lifting of of H to F on yeah. So yeah, it'll. So let me draw the diagram real quick so that it'll be clear. So yeah. So this is the lift. Remember, this is a fibration. So yeah, this commutes. Now further, suppose, okay, oh, wait, sorry. So let me write it like this: is a lift and H epsilon is a, wait, just let me think for a moment. I think this should be fine, but just give me 1 second. Yeah, I think this is fine. Yeah, if it's a lifting of HE, excuse me, to E, that is, yeah. So yeah, drawing this again. Hope I don't mess this up. So remember, this was, yeah, so this is a map Q, okay. Yeah, right. Yeah, so if this happens, then there's a homotopy, which I denote by H bar, which lifts H, that is, we'll get, yeah, lifts H. Yeah, so that is again, and this time, okay, let me give a proof. It's not that difficult. Okay. So yeah, using the previous theorem and like all the given data that we have, so we'll end up with the following. So yeah, I won't get into the details, but I'll just like quick sketch. So we'll get, wait, let me check my notation again. Yeah, so we'll get the following commutative diagram. Okay, yeah, this was epsilon. This was an F. This was also an F. I'm sorry. I don't know. Yeah. Hope everything else is fine. Yeah. So yeah. So yeah, this we will have a filler by the previous theorem. And why? Because this map is anodyne. Yeah. So now, yeah, I see that I'm already out of time. I think it will take 15 more minutes. So what do you guys say? Let me hear some feedback. Can someone put something in the chat or unmute and speak up? Okay, so let me continue. Okay, let me continue. Where was I? Right, yeah, right. So now I'll give a few applications of the covering homotopy extension property. So let me think. Okay, so here's a theorem. If we have an anodyne map. Wait, let me make sure I am not. Okay. Yeah. Yeah. So let me write this from the beginning. That yeah. So wait, what am I calling this? Yeah, I'm calling this J. So from the beginning, yeah. So this is a mono, whatever I call it. So map from A to B will be a mono. So mono in the category of simplicial sets. Okay. So yeah. So if yeah, this is supposed to be A and B, is the anodyne and A and B are Kahn complexes, then X is I mean A is a get this wrong. A is a strong deformation retract. Again, this is like the applications I won't give a proof because I don't have that much of time. Retraction of Y, and if J is a mono, so yeah, that is something that we kind of assume already, but let me write it this way. J is a mono such that X is a, again, it's A. A is a strong homotopy, strong deformation retraction of B, then J is anodyne. Right. So now, okay. So let me just with this theorem again. I want to give a proof. So if K is a Kahn complex, then the map. So let me name this. Yeah, B is. So just let me pause for a moment. Yeah. Then the map say to K is acyclic if P is homotopy equivalence. The proof, I mean, yeah, I'm going to proof. So Okay, let me see now. So yeah, now we are finally about to define the standard canonical model structure. But before that, let me define minimal fibrations. So I'll just give a definition. A simplicial set map Q from A to B, or yeah, I can, yeah, map Q from A to B is said to be minimal vibration if Q is a vibration and for and the following diagram. So let me draw it first. Let me try to recall it for a moment. Yeah, I'm sorry. It's taking me some time. Yeah. I think it should be just a moment. So I'm defining a minimum. So it should be, yeah, right. So this is a map. We call this H. Yeah. So that is so yeah. So this commutes. So yeah, that means the following are equal. So, yeah, so these are equal. Then x is equal. Right. So yeah, we denote this by mod. So yeah, it's like taking mod, right? So yeah, we can like it's obvious that if A is a count complex, then it is an equivalence relation. Okay. So yeah, so I defined it. So yeah, I'll just give a quick theorem again without proof so that you can. So X is a count complex. And there exists a strong deformation rate at, let me call it X dash of X, which is minimal. Again, I won't give a proof. Right. So yeah, let's get to business now. So let me define something before defining the model structure. So suppose it is a map, be a map in special sets. F is yeah, we are defining weak equivalence. So F is a weak equivalence if for all complexes, say K. So the following, we have the following bijection. So yeah, this is what you mean by yeah. So this is what you mean by weak equivalence. So now it's like, it's easy to see that if we have maps say G and F from X to Y, then F and G are homotopic if right. So now if F is a homotopy equivalence, if F is a homotopy equivalence, then this map is a bijection, right? Also, so yeah, for any B. So from this, it follows that if F is a homotopy equivalence, and K is calm. Let me just say is calm. Then this is homotopy equivalence, and yeah, this is a bijection. Right. So F is a weak equivalence. So yeah, we can show that. Yeah, we can show that an acyclic vibration is a weak equivalence, but we won't get to that. So now we can see, like, you know, the way we get, we see that there exists a model structure. So there's some motivation to it. So the previous, like all the things that we did just before, so we can see that we can interpret that as follows, right? So if so, yeah, here's an interpretation. So yeah, this is the way I see it. So if these maps are anodyne extensions with these two X bar and Y bar can, and F dot, right, to be a filler, right? Or yeah, I think yeah, it is a so filler. This is a filler. Just pause for a second. Right. Yeah, so let me draw this clear. Yeah, then F bar. Yeah, right. This is what I was saying. So yeah, it is a homotopy equivalence. So now, so what we do, right? So this was our motivation right here. So now let me write the key theorem, or the main theorem, any way you like it. So in the category of simplicial sets, if we set vibrations as Kahn vibrations, co-vibrations, the collection of co-vibrations as monomorphisms, and weak equivalences as defined above, then we get a proper equivalent homotopy structure. Or yeah, a model structure, whatever. So for proving it again, so yeah, so the proof that I am talking about that is different from the way it's the treatment in Cisinski, but yeah, so all points. So before that, so yeah, so I was not the one who talked about model categories. So let me just quickly write the axioms of model category so that I can prove it. So the way I see it, so that I can prove it the way I want it. So let me call my axioms like this. So model category axioms. So again, yeah, let me repeat. So yeah, people can leave if it's too late, but yeah, let's continue. So right, yeah. So the axioms. So the first, yeah. So M1 is my 342 property, or which I'm not writing because it's really fine. So M2 will be my closure under retracts, and M3 will be my lifting. So yeah, so the thing is that yeah, I'm not citing it in terms of a weak factorization system. So that is what I mean. So suppose we have something like this. So okay, let me just give this. So this is I. So if I is a co-vibration, F is a vibration, and if I or yeah, and if I or F belong to weak equivalences, then there exists a filler. So this is my M3, and M4 will be factorization axiom, like So again, I'll just do dots. So either, so yeah, so every morphism can be factorized as follows. So this right here, so this is either an acyclic cofibration, and this is a fibration, or this is just a cofibration, and this is acyclic fibration. Right, and my M5, let me write it here, would be about push out stress. So yeah, so again, let me draw it like this. So if this W is in capital W, that is a weak equivalence, and so is this W. Right. So dually, like, yeah, push outs of a weak equivalence. So yeah, you can make the, like, yeah, by a cofibration. And so this is a fibration. Yeah, I'm sorry if you didn't mention it. Yeah, so you can dually think of it in terms of a cofibration, right? So yeah, so now I'll state two lemmas that I'll use in a way to prove that we have a model structure. But yeah, so they're a bit involved. So at least the first one is a bit involved. So I won't give a proof. And yeah, so let me state them. So let P to be an anodyne extension. And you think of a bundle, have different bundles. Then there exists a pullback square. So again, let me make sure I don't get my notations wrong. Mixed, yeah. So such that, so yeah, this is a bundle. Wait, no, it's B. Or let's hang on. Right. Wait. No, I think it's so just B is a bundle. Or wait, let me give it a thought. I'm missing something. Let me try to remember. No, it is B. Yeah, it's fine. And yeah, sorry. And this morphism that you have, this one, is anodyne. Yeah, and also I'll just say this extension is unique up to isomorphism. Don't forget that. And the second lemma that, okay, so let me call it 1. So lemma 2. So now instead of a square, we'll have a cube. So let me try and draw it properly. So, okay. Hope I don't completely mess this up. Yeah, this is turning out to be better than I'd expected. Right. So yeah, it is a commutative cube such that, yeah, in of course in simplicial sets, such that the left hand and the back faces are pullbacks. So okay, let me denote the pullbacks by shading them. So pullbacks by shading them. So this is a pullback square, left one, and the back face. So hope that doesn't mess. Oh, okay. Let me. Oh, messed it up. Let me try and see. Let me try and use a different color for this one. I'm sorry. Should have seen that before. Seems to be totally messed up right now. Okay. So yeah, let me use a different color. So yeah, this is a. So these are pullback squares that you have. So the left one and the back one. And A to B is, so if A to B is a mono, and the top and the bottom are push out squares. So I don't know. So for the pullback ones, okay, I'll use green, and for the push out squares, let me use something else. Use, I don't know, blue. So I'll use blue. So the top ones, this one I'll try to do vertically so that it's a bit comprehensible. These are push out squares, right? Then the right and front faces, the ones that are left, are pullbacks. Right and front faces are pullbacks, pullback squares, of course, right? So, okay, right. So now I'll give a proof of the main theorem. Again, I won't prove it completely, but yeah. So the axioms that I stated, so M1 and M2 are clear. I mean, yeah, it's obvious. And M3, yeah, I think it's subscript. Yeah, M3 follows by definitions of acyclic fibrations and acyclic cofibrations. You can check that. And yeah, and Q4 needs a bit of work. No, I mean, yeah, Q5, sorry. Q5 needs a bit of work, which I won't do right now. Bit of work, which involves minimal fibrations. So yeah, I can find a proof. Yeah, I'll give a reference for the proof. And yeah, Q4 follows by two of our previous lemmas that I had stated quite like almost at the beginning that I'd said will be useful a bit later. We get to them real quick. So these two ones, this theorem and its corollary, like you have this sort of a factorization. Right? So we can use this to prove Q4. So by that we get a model structure that is called the Kahn-Coulomb model structure. By previous results. So now, I don't know, it will take some time. Now I'm yet to talk about the X infinity functor, Kahn's X infinity functor, and anion extensions. So there are two things. So I guess, let me continue. So people who can leave. Sorry about that. So, okay, so let me quickly let me like quickly give an idea about it. So yeah, it is basically it's like of a combinatorial construction that associates a Kahn complex, right? So we'll prove that this is a Kahn complex for X simplicial set. So it associates to a Kahn complex an arbitrary simplicial set up to natural weak equivalences. I mean, that is the idea, right? So okay, so let me get to business. So the non-degenerate simplices of this. So yeah, they form a poset that I denote by this, for by like obvious order relation that I'm not getting into. This is obvious. So right, and yeah, we know that. So this is isomorphic to this, right? And okay, so let me define the nerve of the poset to be this. I'll explain why I call it SD real quick, because this is literally the, so yeah, this is the SD stands for subdivision. I'll give a few examples as well, but let me just define as the subdivision the way you are supposed to think of it for an arbitrary simplicial set, right? So not just standard and simplicity. So for a simplicial set X, so this will be the colimit like this, right? So this is my definition. Oh yeah, maybe. So Let me give an example. I'm not sure if I'll not mess it up. Subdivision of delta 2. God. Please make me know if I commit a mistake. So I think it should. Because yeah, this is something I'm doing right now. I'm not written it before. Yeah, this seems to be the. So it is like a Betti-centric division. So yeah, I won't get into the details because I don't have time. So now let me define the x functor for a simplicial set X. We define by okay. So right. So yeah, an observation. So since we have an isomorphism of this form for a simplicial set, arbitrary simplicial set Z. So this x functor that we have, something that I didn't mention. So Kant's original paper on the x functor that you can find on NLab or anywhere. So yeah, that's worth a read. Is right adjoint to the subdivision factor. Right. So okay, let me define a few more things before wrapping up this section. So the last vertex map, this is the way I call it. So let me call it LV for last vertex. It's the map induced by the maps of posits. So yeah, so this map is like, I mean, yeah, it's easy to see. So yeah, this so similarly we can extend this to a simplicial set. So this extends to give a map, right, for a simplicial set. So X is a simplicial set, right? So again, yeah. So adjoint to LV, which is my least vertex map. So adjoint to LV is the map. So yeah, let me name it J because I'll be using it. So again, X is simplicial. So let's consider the following directed system. So yeah, we are getting to the construction of X infinity. So this is the directed system that I'm considering. Right, so you continue. Now you just take the co-limit. So and you denote the co-limit. We denote the co-limit by infinity. So yeah, I'll state a few things, but we won't give a proof. Okay. So yeah, I was thinking of proving this, but I don't have time. So it is a Kant complex. So X infinity is a Kant complex for any simplicial set S. So I'll give a proof again. So now a crucial result. So for any, I don't know what to call it. So let me call this lambda. So we have a map from horn, kth horn to extension of X. So there exists an extension. So yeah, this is obvious. So you can extend it to, so you can basically extend the horn to the standard n simplex. So yeah. Also, again, I won't prove it. So you can prove that the x infinity functor preserves fibrations, finite limits, and zero syntheses. So yeah, so I'll just speak briefly about enine-anodyne maps and then we'll wrap it up. I'm terribly sorry for extending this so long. Enine-anodyne extensions. Okay. So let me define enine-anodyne extensions. So I'll just, so yeah, I mean, there are different, so Cisinski does it in a different way, but I mean, this is the way I think of it. So I think of it as a closure of the saturated class generated by on inclusions. Correct. Right, let me, sorry again, let me try to remember. I hope I'm not saying this wrongly. Okay, just let me pause for a second. Yeah, I think, yeah, we can think of it like that. Super sure, but yeah, this is the way, yeah, I think, yeah. On inclusions, right, not just on inclusions, yeah, this is correct. So again, I'll just prove the following, that the following class of morphisms coincide. So let me name them. So the class of inner anodyne extensions. So let me call B2 smaller. Yeah, this is exactly from Cisinski. So you can look that up. Smallest saturated cluster, which I don't need to say actually, generated by, yeah. So this is my second one. The third one is again the smallest saturated class generated by. So yeah, define what K and L are for any mono. So it is, so you just have a monomorphism. So yeah, I want to go for this. So okay, now I'll define the inner fibrations. So a map P is said to be an inner fibration if it has the right lifting property with respect to the saturated class generated by on inclusions, which is like the class of anodyne extensions. I don't know why I just said this. So yeah, so you can also check that this claim, the morphisms with the left lifting property with respect to all inner fibrations are precisely inner anodyne. So a corollary would be, yeah, so it's a long corollary. It is a part of the last corollaries that Cisinski talks about. So yeah, maybe I'll stop here then.
In the house,
thanks.
Oxford, UK. Hello.
Let me stop the recording.
Hi, family.